last week we established that the work energy theorem says that work is equal to the change in kinetic energy, right, of any kind of object. Work is the change in kinetic energy. Because in order for the kinetic energy to change, you need work. And in order for there to be work, you need a change in kinetic energy. Or in some form of energy. Because now we're going to take a look at the second part of that law, which says that work is equal to negative delta UG. And I'm going to go ahead and leave it up to my smart students to interpret this for me. So let's go ahead and ask Mr. José Eduardo. W es igual a menos delta UG. What's that?
The changing gravitational potential energy.
Well done, José Eduardo. So work is the change in gravitational potential energy. Did I have a question? No? Okay. All right. Now, you say, again, Mr. Mian, this isn't making any sense. What does that have to do with what I'm doing? Well, the best thing that I can do to explain is, let's go ahead and let's do a problem here. Let's do a problem so that we can understand. So you see example 9-7 there. I'm going to read it to you. A student lifts a 0.75 kilogram book from the floor to her 1 meter high desk with a constant velocity. Later, she moves the book at a constant velocity to the bookshelf 2 meters above the floor. So A, how much work did she do in the first lift, in the second, and what was the change in the book's gravitational potential energy? So let's go ahead and draw it out. You have a student there that has a book with them. And the example, you have a young lady, so let's go ahead and make it a young lady. There we are. And so she dropped the book, and the book was on the floor. And then she grabbed the book and she put it on top of a shelf, which on her desk, which is 1 meter tall from top to bottom. There we go. And so she grabs this book and she puts it on her desk here. Very nice. Okay. And then for some reason she decides that she doesn't like it there on her desk, and so she's going to lift it higher than the desk because her desk has too many things on it, right? And so she's going to put it on a shelf up here, which is 2 meters above the floor. So it's 2 meters from top to bottom. There we are. So she's going to put the book there. And we'll call this A, position A, and we'll call this position B. Okay? Now the book weighs 0.70, well, not weighs, but it has a mass of 0.75 kilograms. Okay? So what is the question that this problem is asking? How much work did she do to lift the book from here to here? How much work did she do to lift the book from here to here? Well, that's really easy. How do we find the work done by this student? Well, you say, oh, Mr. Mian, I know that one. That's old hat, as a British expression goes, old hat, which means you've already seen it 1,000 times. Okay, work is equal to force times distance times cosine of theta. Sale vale. Do we know the distance? Yes, we do. Do we know the cosine of the angle between the force and the distance? Yeah, it's 0, because they're both pointing up. Do we know the force, Mr. Galt, applied to this particular book here?
No.
We don't, right? And the problem here is that they use a word there, or 2 words, called constant velocity. And Mr. Galt, why does that impede our ability to find work, that word constant velocity?
Because we don't have force.
Well, because we don't have a force, because we don't have?
Acceleration.
That's right. Well done, Galt. So then constant velocity means that there is 0 acceleration, or that there is no acceleration, right? So then the people writing the book, they knew that you guys were going to be like, oh, well, I can use this formula. And so they're like, no. She lifted it at a constant velocity, so then you can't use that formula. Which means, darn, Mr. Mian, how on earth are we going to solve this problem? Well, thankfully, we just learned of a very nice equation, which says that work is just a change in gravitational potential energy. And you say, well, Mr. Mian, that sounds kind of hard. That shouldn't be. Let's go ahead and take a look at this one, right? So we're not going to use this one. Rather, we're going to use W is equal to the change in U. Right? Not the change in U as a person, but rather the change in U as in gravitational potential energy. Now, let's use a little bit of common sense. Jose Luis, how much gravitational potential energy does the book have lying down there?
0.
That's right, because it's not lifted at all. There's no potential for him to fall because he's already on the floor. Literally, physics supports the idiom, once you hit rock bottom, the only way you can go is up, okay? So when you're at the lowest point, can't go any further, so just keep going up. Now, what is the gravitational potential energy there? Well, by logic, it has to be 0. Lógica, ¿verdad? Que aquí el libro en el piso no tiene energía. But if we wanted to prove it using math, you would just say mg times h. What is my mass? It's 0.75 kilograms. What is my gravity? 9.81 negative, right? But what is the height of this book? La altura is 0, right? It's 0 because the book is on the floor. So then anything multiplied times 0 is?
0.
Which then supports our logical conclusion. That makes sense. I didn't do any math at first, right? It was just logic.
So what decimal are we rounding to?
With 0,
No,
none
I'm
of
talking
them.
about like to the one.
Just use the first decimal point. Very good. But now
7.4.
she lifted it to the second position, which is a meter above the ground. So now how much gravitational potential energy does the book have?
7.35.
Okay, we have an answer already.
7.4. You said rounded.
MGH. So then we have 0.75 times 9.81 negative, of course. That's kilograms, meters per second squared. And what is the height of this book now? It's 1 meter, right? Because it's on her desk. So times 1 meter, it doesn't really matter for our calculation, but it does matter for the units. So what is 0.75 times 9.81 times 1 is?
7.357.
7.4.
4.
Right, 7.4. Let's round it to that. 7.4 what?
Joules.
That's right, joules, because it's an energy, right? Now the quick question here then is how much energy did I gain gravitational potential energy from going from the floor to up here? Well, 7.4 joules, because the difference between 0 and that is just 7.4, which means, Diego, that the work done by this person to lift it from the floor to the desk is what?
7.4 joules.
No, work is equal to negative change in U of G, right? So then that means that you get the initial, what is the initial energy that this book had?
0.
And the final energy?
7.4.
Okay, so then, all right, yeah, then that balances out and gives you 7.4.
Hey!
I apologize, very good. And basically we're going to do the same thing with, we're going to go ahead and do the same thing with the shelf. Now, Allison, I'm going to now raise this book up to the top shelf. And I want to know how much work I did there. What's your plan?
Change out the 1 for 2.
Good. Okay, so Allison says, well, first off, let's find out how much potential energy is here. So let's do it. U of G is equal to mgh, which is basically the same thing as we did down here, but instead of 1, we're going to go ahead and multiply it by 2. Or if you know your math, you know that you're basically just multiplying this number by 2 as well. So let's go ahead and multiply him by 2. And what is the answer here?
Negative 14.71.
14.71. So let's go ahead and say 14.7. Very good.
How do you take it out?
So my student now realizes that this book now has a potential energy difference of 14.7, which means how much work did she do to lift it from here to here?
7.3 joules.
Same thing, right? That makes sense because the difference between heights is the same. And if I lifted it 1 more, what would be the difference from... Right, no, what would be the difference, I'm sorry, from this position to another meter tall? Would be 7.3, it would be the same thing, right? So then work, remember, is equal to the change in gravitational potential energy. How much energy did I have to start with? 7.4. How much energy did I end with? 14.7.
So, but it would be 7.35.
Negative,
That's why it's 14.
negative 0.74. And then that would be positive 7.4 joules. There it is. So in this case, it just works out that the numbers are the same. Okay? Hopefully you didn't let that intimidate you. Any questions?